Hi guys, Harry here. Welcome to Scrap Science. Right, extracting lithium from lithium-ion batteries. You know what we're doing. This is the second video in this project, so if you haven't seen the first one, you should go and watch that now. So where we're at right now is in the last video, we took the electrode materials out of about 160 watt hours of lithium-ion batteries. We then took the electrode materials and put them in a furnace, heated them to 1000 degrees to get rid of any plastics and any volatile solvents. And what we were left with is this oxide mixture from the electrode materials. In the last video, we unsuccessfully tried to extract or leach out the lithium in here with distilled water. That obviously didn't work. That's why we're back here today. And luckily I have a plan B, but it is a lot more complicated. Currently, the oxide mixture here is a pretty big mess of things right now. It's got the oxides of basically all of the metals that were present in the battery. So that's manganese, nickel, cobalt, lithium, maybe even copper. We've got some aluminium metal in there, maybe some aluminium oxide as well. And we also have a bunch of graphite from the battery and from the furnace itself. And we probably have a whole bunch of paper that I've chucked in there because I was using that to filter things as part of the process in the last video. So the basic plan to process all of this material and extract the lithium is to first dissolve up all of the metal oxides and metals that are in here with some acid. This will leave behind the graphite and the paper so we can selectively bring all of our metals into solution. So I think we're just going to dissolve everything up in sulfuric acid. I have here some 4 molar sulfuric acid that I made quite a while ago. Hopefully this will be enough to dissolve all of our oxide mixture, but if not, I do have some more. Right, we'll just start with a little bit of sulfuric acid. Yeah, looks like the reaction is somewhat vigorous. There are probably some carbonates in here, and additionally there is aluminium metal, both of which react with sulfuric acid to generate gas, so we do kind of expect this to happen. A couple of weeks later, what I have been doing over the past 2 weeks is incrementally adding some dilute sulfuric acid to our solution, just the same as you saw in the beginning. Eventually, what would happen each time is the solution would eventually return back to a neutral pH due to the fact that the sulfuric acid I'm adding is being used up in the dissolution process. In this time, I have added around a few hundred milliliters of dilute sulfuric acid to our oxide mixture, and we still haven't dissolved everything up. I can tell because the solution has returned to neutral once again, but I'd like to stop here and move on to the next stage of the process, because I think it'll be a good idea not to do the full thing in one go. Maybe we'll just use this little batch to check that our process is going to work, and then we can always come back and dissolve the rest of our oxides later on. It's also good because the next stage of the process, it works better if our solution is neutral. So we're already there. What we can do now is filter off all of the remaining oxides and the graphite that's left behind, and we will just have our sulfate solution with all of the cobalt, manganese, nickel and lithium for further processing. For filtering, we now have the capability of using my fancy new vacuum filtration setup. It's not very fancy, but it is orders of magnitude better than a paper towel filtration. So right away, we're just going to filter this solution. With that, you can now actually see the lovely red color of our solution from the cobalt that we have in there. And it's kind of interesting because other people who have dissolved up the oxide content of the lithium batteries tend to get a green solution, but these batteries that I'm processing right now must have more cobalt, or at least less nickel, than other people's have. I will continue filtering this. Looks like it's going to take a while until we have gone through our entire batch. There it is, all filtered. It looks black on camera because it is very concentrated in cobalt, I assume. In reality, it looks like a very, very dark red, just on the edges of the flask there. You should be able to see that red color. If we now transfer it to a separate vessel, yeah, there you go. With this solution now, what we can do is move on to the fun stuff, because we now have all of our electrode materials, all the metals from our electrode materials in solution as sulfate salts. So that's manganese, nickel, cobalt, lithium, and a bit of aluminium, all in solution here. And we need to get rid of everything but the lithium before we can drop the lithium out. Anyway, the first metal that we want to remove from this solution is manganese. And to get our manganese out of solution, all we need to do is oxidize it, convert it from manganese sulfate into manganese dioxide. So the way I'm going to do that is I've heated up the solution to near boiling, and then off to the side here I have a small solution of ammonium persulfate. It hasn't all dissolved yet, but this is a strong oxidizing agent and should be able to oxidize our manganese to manganese dioxide at these high temperatures. So I'm just going to add this just dropwise now that we've got our solution hot. And with continual additions of our oxidizing agent here, we should eventually start to see manganese dioxide precipitating out. And yes, I do believe this has worked. You can probably even see on camera that the solution has gone from a very, very dark red to a deep brown color. That brown color is obviously our manganese dioxide that's now precipitated out. So hopefully I have precipitated all of the manganese as manganese dioxide, and we can move on to filtering it off. Note the fact that the color of the solution that's passing through our filter now hasn't really changed all that much from before. And that's because the manganese in our original solution wasn't really contributing to the color all that much. So we get the same kind of color from our solution now that we've removed the manganese. At the end of our filtration, we're left with a beaker which is clearly stained with a whole bunch of manganese dioxide. I'm going to have to clean that out at some point. I'm not quite sure how I'm going to manage that, but I'll find a way. We are also left with our filtrate, which has a bunch of stuff crystallizing out in the bottom. I'm not sure what that is. I'm going to leave that in there just in case it contains any of our lithium. But I'm thinking maybe it's aluminium sulfate crystallizing out because the sulfate concentration in this solution is so high, it's dropping out. And the residue in our filter is manganese dioxide. And this manganese dioxide should be quite exceptionally pure. I mean, it'll be much more pure than anything you get out of, I don't know, a lantern battery or something with graphite particles and other oxides of manganese mixed in with it. Probably purer than most sources you can get it from. So definitely worth hanging on to that. Right, disaster has struck. I didn't get it on camera, but in the middle of filtering off, doing a second filtration of our manganese dioxide, this happened. You can see that there, with a whole bunch of solution in our vacuum flask. The bottom just cracked and popped inwards. There was a big bang and all of our solution spilt all over the desk. I was able to mop it all up and do a washing of the desk, so we've got all of our solution back, I'm pretty sure, but this is it now. I have a beaker full of paper towel that I used to mop it up, no doubt contaminated with whatever was on the bench before. Honestly, this is quite possibly the worst thing that could have possibly happened, because while I was able to mop up all of our solution of cobalt, nickel and lithium and whatever else we have, we've now introduced the contamination from whatever might have been on the desk before. And really the worst thing is, now that we've got all of this paper towel that I've mopped up everything with our solution in it, I'm going to have to wash it like 3 or 4 times to get all of our transition metal lithium goodness out of it. And that will require, multiple litres of distilled water, which I have, but then We were doing so well before with 500 milliliters of solution, going from 500 milliliters and diluting that down to, what, 3, 4, maybe even 5 liters. That's a lot of water to boil off. I am pretty annoyed, and in hindsight, I probably shouldn't have trusted this cheap Chinese glassware, and maybe I should have put a dish underneath it, because I was kind of expecting it to happen, possibly, but oh well, that's just a lot more work that we have to do. Yep, pretty big disaster, I would call this. We have turned 500 milliliters of solution into 3.5 liters through this little mistake. That's going to be fun to boil down tomorrow. I think I did a pretty good job mopping up all of the spilled solution and washing all of the towel that I was using to mop it up. These are the paper towels I used. I washed them through 4 times to give us this 3.5 liters of solution, and I would say that I have recovered definitely more than 90% of all of the cobalt, nickel, aluminium and lithium that we spilt. So, not too big of a loss, but it is a waste of 2 days of work just to bring us back to where we were before. So very, very disappointed. But as soon as we boil this down to the volume that we had before, we can just completely forget this ever happened. And I'm very much looking forward to that. Nearly 2 days later, after a lot of boiling down, we have reduced that 3.5 litres back to maybe a little bit more than 800 millilitres, which I'm perfectly happy with. And as I said, we're just going to completely forget that this mistake ever happened, and we're going to move on. So as I was going to say before, we have now removed all of the manganese from solution, and we have extracted it as manganese dioxide. So we were able to extract around 20 grams I have here of very pure manganese dioxide, which will be helpful later on if we ever need that for anything. As a result, what we have left in solution is, of course, our lithium. We also have possibly a bit of aluminium from the electrodes, as well as cobalt and nickel in solution. We can tell there's a whole bunch of cobalt in there because it is very, very red. Right, anyway, the next step in our plan was going to be to electrolyze our solution here. What this was meant to do was remove both the cobalt and the nickel, both of the remaining transition metals, by plating them onto the cathode. I gave this a go, and I'm afraid we didn't really get much. This is the cathode I used. We did get something appearing on the cathode, but after 2 days of relatively high current electrolysis, we really weren't getting any plating occurring on the cathode there. So I'm pretty sure I know what went wrong, and that is the fact that the solution is too acidic. There are too many hydrogen ions in there, and as a result, the cathode reaction that generates hydrogen gas is favoured over the plating of the cobalt and the nickel. Now you might think it would be easy to just neutralise the solution and electrolyse that. I could just add ammonia to the solution and neutralise the sulfuric acid that way, and it'd be no big deal. However, the issue here is that the electrolysis itself is going to generate acidic conditions as it runs. So as we plate out the metals from solution, the anode reaction generating oxygen gas would be generating hydrogen ions, which would be put back into solution, slowing down our electrolysis once again. So the only way that we could feasibly do this is with some kind of pH buffer, but at that point the electrolysis procedure just becomes extremely complicated, and the entire point of using electrolysis from the start was that we weren't going to have to add any extra ions to solution in order to do it. It would be just a removal step of the transition metals, whereas if we have to add a pH buffer, that doesn't really fit with the idea of just a nice clean method that doesn't add anything to solution. So as a result, I've been looking for another method to remove the transition metals. The question is, can we find something to do to this solution that will A, neutralize the sulfuric acid, B, remove all of the transition metals, and C, do it without adding any extra ions to solution. And as it turns out, I think I've found something we can add that will do all three of these things. The answer here, I think, is calcium hydroxide, which I've bought online, as you can see. What I'm thinking will happen if we add this to solution is the calcium hydroxide will react with the excess sulfuric acid to neutralize it and precipitate as calcium sulfate. It will precipitate all of the transition metals as hydroxides. And since both calcium hydroxide and calcium sulfate are insoluble pretty much in water, we won't be adding too many ions to our solution. Additionally, calcium hydroxide has the added benefits that it will also drop out any aluminium in solution, and it will do all this without adding any sodium contamination to our process, which we have tried our absolute hardest to avoid this whole time. So overall, I think this is a pretty good method, a pretty good replacement for electrolysis for dropping out all of our transition metals. So I'm going to give it a go. I know a lot of people were keen to see some electrolysis of cobalt and nickel, and that is just going to have to wait for a future video. I promise we'll get around to that. In a future video, I am planning on separating the cobalt and the nickel from the precipitate that we get from this step. So you can look forward to that at some point in the far future. Starting on a small scale, of course, we'll just add a bit of our calcium hydroxide, just like that. And then I'll give it a proper stir around. You can see that neutralizing the sulfuric acid, and if we keep stirring, we should see a whole bunch of precipitates. Eventually, on addition of enough calcium hydroxide, the solution fills up with a whole bunch of precipitate. It starts to smell like ammonia because we have ammonium ions in solution, and the pH turns basic. So at that point, we have finished precipitating out all of the necessary transition metals along with the aluminium, and it's ready for filtration. But before we get on to that, I will process the rest of everything. Okay, so I've added calcium hydroxide to our entire stock of solution, and we have reached the point where the solution is now basic and smells like ammonia. So that means that we should have precipitated all of the transition metals and aluminium, leaving just ammonia and lithium in the form of a sulfate and hydroxide in solution. So the next step is to filter out the precipitate, because that's what we don't want. But I'm going to tell you now, it's going to be very tricky because our precipitate is calcium sulfate mixed with cobalt hydroxide and nickel hydroxide and aluminium hydroxide, and all of those things are an absolute nightmare to filter. Sorry about the noise of the pump, but as it turns out, the filtration, vacuum filtration, actually works far better than I was expecting. You can see the rate of our filtration there. It's going a lot faster than I thought. So this is very exciting. And then even more exciting is the fact that the solution we're getting, we have nearly 400 milliliters of it now, is perfectly clear. So there should be lithium in there without any other contaminants other than ammonia, which doesn't matter. Anyway, it shouldn't take too long to filter the rest of this. So I'll update you once it's all finished. Alright, now finally, at the end of all that filtration, we have isolated our precipitate. This is a combination of calcium sulfate, nickel hydroxide, cobalt hydroxide, and aluminium hydroxide. We will work with this in a future video where we will actually purify and extract the cobalt. But that is a project for the very far future, because I am quite sick of this project taking up my time, but we will get to that eventually. So I'm going to put this to the side and come back to it. And this, as you can see, is our liquid that we obtained by filtering that mess of precipitate that we had before. Originally, we had about 1.2 litres of this because I did actually wash this stuff 3 times with distilled water. But I've just spent the last few hours boiling this down, and now we're left with around 500 milliliters of what should be a solution of lithium hydroxide, lithium sulfate, and ammonia. You can probably tell from the color that there are trace amounts of probably cobalt and nickel in there as well, but I'm not too concerned about that really. But overall, We have done the hard bit now. We have purified the lithium to the highest extent that we can, and now all that's left to do is precipitate it out. So as I said before, I've concentrated the solution down to 500 milliliters, which should help us precipitate out our lithium. We're going to precipitate it, probably as you know, as the carbonate, and to do that we're going to add some potassium carbonate. We'll get a double displacement reaction and the lithium will drop out. I'm not too concerned about potassium contamination because potassium doesn't have a very bright flame color, and a flame test is how we're going to be testing our lithium. If we had sodium, say we were using sodium carbonate to precipitate it out, I think that'd be a bad idea because the sodium would dominate the flame color. But I have here some potassium carbonate, about a 30% solution in water, and when I'm ready, I'm just going to add this straight to this solution while it's hot, because the hotter the solution, the lower the solubility of lithium carbonate, and once we add this, we should see a precipitate start forming. I'll turn on the stirring, and then we'll add some of our potassium carbonate. Oh yeah. You'll notice that the solution has kind of turned purple and there is a bunch of precipitate in solution now. I've done a little bit of testing and the purple color seems to be in solution. It seems to be some kind of cobalt complex, I'm thinking. So that's not the color of our precipitate. I think our precipitate should be our lithium carbonate, which I'm going to go ahead and filter right now. Alright, did I say before that the solution was going to be purple and the precipitate was going to be white? Because that precipitate is definitely purple. There's no question about that. I've washed it a couple of times with distilled water and that is not losing its purple color at all. So disappointingly, I do think this is mostly lithium carbonate, but I do think there is quite a bit of transition metal contamination in there, which is disappointing. And additionally, we were expecting a full 60 grams of lithium carbonate out of this process, and I'm going to tell you that is not 60 grams. That, is maybe 1 gram at best. So I don't really know where to go from here. I'm pretty sure the lithium isn't there. We would have been able to precipitate it out as the carbonate. It's possible our lithium is in here, which would be a bit of a disaster because that's pretty much where everything else is. It's also possible that we were never able to dissolve the lithium in the first place from our oxide mixture out of the furnace. It could still be just in there. I'm honestly not sure. I suppose we'll do a flame test of this stuff to see whether it does contain lithium. But otherwise, it is kind of back to the drawing board once again. I suppose there'll be a third episode at some point in this series of lithium extraction videos, if I ever get around to doing that. Honestly, I think this is making me go a little bit insane, so I'm going to take a very long break from this project regardless. Well, would you look at that yield? All of that precipitate that's probably not even lithium. I suppose it's flame test time anyway. Well, that didn't really look like lithium to me. I'll tell you what I think happened. I don't think this is lithium at all. I think this is a mixture of calcium carbonate and cobalt carbonate. I reckon we had trace amounts of cobalt and calcium in solution after trying to precipitate everything out. I don't think there was any lithium in our solution because it would have precipitated out as the carbonate. We would have expected that and we would have seen it in the flame test. So now we've come to the end of the video, and this is normally the time where it's good to reflect on how our project's gone. You might ask, was it worth it to, first of all, spend hours ripping apart lithium-ion batteries to get to the oxide mixture that contains the lithium? Was it worth it to put all that in the furnace, spend hours trying to reduce its volume and convert it all into oxides? Was it worth it to spend weeks dissolving up that oxide mixture in sulfuric acid? Or to spend days trying to recover our solution from the table when that glass shattered and it spilt all over everything? Was it worth it to buy calcium hydroxide specifically for this process so that we could precipitate out all of our transition metals? Was it then worth it to spend days filtering out that solution and boiling it down to get it to the point where we had the hope that we'd get just a few crumbs of lithium out of the solution once we precipitated things out with carbonate? Was all of that trouble that we went through worth it to receive just this tiny little bit of product that probably doesn't even contain any lithium? And I'm going to give you the answer to all those questions. It's no, it wasn't worth it at all. If you're thinking that you're going to extract some lithium from some batteries yourself, I have one bit of advice to you, and that is don't follow any of the methods that I have put forward in these couple of videos. Follow someone else's method and maybe have some hope that you'll actually receive some yield of lithium carbonate at the end. Regardless, I do have some small amount of hope that maybe we might just have some lithium in this precipitate here, in which case it just means there's more chemistry to do, really, and who could be upset about that? Once we get around to extracting and purifying the cobalt, as I said before, we will check if there's lithium in here, but I don't have particularly high hopes. So you can look forward to that video in the future, from when I decide to make it, which will be a long time away, as I've said. But until then, I'll see you later, hopefully for a project that has, a higher chance of success.